This video is a part of lecture series for third semester students. This lecture is about the concepts of the course entitled as Digital Electronics and Logic Design, having course code ECE 313T. Here are the contents that I will discuss in this lecture. First, it is the introductory part. We know that whenever digital data is transmitted from one location to another, some transmission errors occur. These errors are because of the noise present in the channel. Due to these transmission errors, a signal transmitted as 0 is received as 1 or vice versa, leading to unreliable data transmission. Like here, bit 0 has changed to bit 1 due to the noise present in the channel. So it's very important to detect and correct the errors present in the received data. There are actually various codes available which can be used for error detection and correction. First, let us consider error detection codes. These codes can only detect the presence of error. The most common error detection code is parity code. Here in parity code, an extra bit known as parity bit is attached to the transmitted data. Like here, this is the data which is to be transmitted, and this is the parity bit which is attached to this data. This parity bit is attached in such a manner so as to have number of ones in the resulting code, either even or odd, leading to either even parity or odd parity. This parity bit is selected in such a manner so as to have the number of ones in the resultant code either even or odd. Here we have adopted even parity, so the number of ones in the resultant code must be even, that is 4 here. So bit 0 has been appended as a parity bit. Now the process of attaching parity bit is described here. At the sending end, the message is applied to the parity generator circuit where the required parity bit is generated. Like here, this data which is to be sent is applied to parity generator which generates the parity bit, and that parity bit is appended to the data, and this whole message is then transferred to its destination. At the receiving end, the received message is applied to the parity check circuit. Like here, this is the received data, and this is applied to parity checker which checks the parity of the received data. Now if the checked parity corresponds to the adopted one, that is either even or odd parity, then no error has occurred and the original data is received. But if the checked parity doesn't correspond to the adopted one, then an error must have occurred, and we need some error correcting code in order to get the corrected code from the received data. Parity code can only detect odd combination of errors like 1, 3, 5. It can't detect even combination of errors. Till now it was all about how to detect an error. Now let us consider error correction codes. The most common error correction code is Hamming code, named after the person who devised this code. In Hamming code, k parity bits are added to n-bit data word, forming a new word of n plus k bits. The number of the parity bits, that is k, must be chosen such that the k satisfies this inequality, where n is the number of the bits present in the data word. The bit positions are named in sequence from 1 to n plus k. The positions which are numbered with powers of 2, that is 1, 2, 4, 8, 16, are reserved for parity bits, and the remaining bits are the data bits. For example, here n is equivalent to 4, that is there are 4 bits in the received data word. For n is equivalent to 4, we have k is equivalent to 3. This value of k is evaluated from this inequality equation. Now, the bit positions are numbered in sequence from 1 to n plus k, that is 7 here. Further, the positions 1, 2, 4, these are occupied by the parity bits and the remaining are occupied by the data bits. Now let us encode this binary number into even parity Hamming code. Here n is equivalent to 4, that is 1, 2, 3, 4. So for n is equivalent to 4, we have k is equivalent to 3, which is evaluated from the inequality equation. Therefore, n plus k is equivalent to 7, that is 4 plus 3, 7. Start it numbering, it's 1, 2, 3, 4, 5, 6, 7. Further, positions 1, 2, 4, these are occupied by the parity bits, as I said earlier, and these remaining positions are occupied by data bits. Now, in order to get the Hamming code, you have to get the values of P1, P2 and P4. And for this we have a tricky table here, like P1, P2, P4 parity bits are placed here and the data bits are placed here. You have to create some horizontal combinations, like 3 is formed by 1 and 2, 5 is formed by 1 and 4, that is 4 plus 1, and 6 is formed by this and this, and 7 is formed by 1, 2 and 4. Now you have to see vertically, like P1 depends upon D3, D5, D7, D3, D5, D7. You have to do the modulo addition of these data bits and this will give you P1. Similarly, P2 depends upon D3, D6, D7. Again, you have to do the modulo 2 addition, or you can say the XOR operation of these bits, and you will get P2. Similarly, P4 depends upon D5, D6 and D7. This modulo 2 addition of the respective bits, and this will give you P4. Now you have to put these values, that is P1, P2 and P4 in their respective positions, that is 1, 1 and 0. So this is the required Hamming code of this binary number. Moving ahead, Hamming code has a feature that it can not only detect an error but it can also correct an error. Actually, at the receiver, check bits C1, C2, C4 are calculated from the received code word, and if error has occurred, then the decimal value formed by these check bits C4, C2, C1 gives the location of that error, and on complementing that error bit, the received data is corrected. This method is explained here in this example. It's like 7-bit Hamming code is received as this. So you have to find its correct code. It means that this code has some error and you have to find the correct code. First you have to write down this code like this. It is H1, H2, H3, 4, 5, 6 up to H7. 1, 2 and 4. These positions are occupied by parity bits and rest are the data bits. Now you have to calculate the check bits. For the values of the check bits, you have to again create a tricky table. Like here we have H1, H2 and H4, H3, H5, H6 and H7. Again perform some horizontal tricky combination, like 3 depends upon 2 and 1, 8, 5, 4, 1, 6, 4, 2, 7, 4, 2, 1. Now see vertically. C1 depends upon H1, H3, H5, H7. H1, H3, H5, H7. So you have to do again the modulo 2 addition and you will get the value of C1. Now C2, it depends upon H2, H3, H6, H7. So it's H2, H3, H6, H7. Perform the modulo to addition of the respective bits, and this will be C2. Now C4, H5, H6, H7. Again perform the modulo to addition of the respective bits, and you will get C4. Now the combination formed by these check bits, that is C4, C2, C1, is 0, 1, 0, which is decimal 2. So bit 2 is in error. It means that this bit is in error. So in order to get the corrected code, you have to complement this bit. So it is 1, 0 is written here, and this is the corrected code of the received code. Here some review questions are given that you can do in order to better understand these codes. So this was all about error correction and error detection. Thank you.